Hi, I'm Mr. Miller, and this is a lesson on characteristics of polynomial functions. So here is a little exploration in Desmos, and we'll read the instructions. It says, for each degree of polynomial, consider all examples within the folder to discover what determines the end behavior, the number and nature of zeros, and the difference between general and factored form. So let's start with the constant functions. These are polynomials of degree 0. So here's one example. We've got y equals 4. Here's another example. It's y equals -3. And here's a third example. It's y equals 0. So for starters, let's talk about end behavior. You'll notice that all three of these functions are just horizontal lines. So the end behavior I would describe as starting from the left end and extending to the right and maintaining the same position vertically at y equals 4. Same thing with the other ones. So the block graph extends from the left end to the right horizontally all the way across, maintaining the same vertical position at y equals -3. And finally, we've got the red graph, which extends from the left end to the right end, always maintaining the same vertical position at y equals 0. So that's the end behavior. The number and nature of zeros, well, what you'll notice about the purple graph is that there are no zeros. And the black graph, also, there are no zeros. So those two are horizontal lines. They never touch the x-axis. They never cross the x-axis. Now, the red graph is right on the x-axis. So it touches the x-axis everywhere. So it has infinitely many zeros. And of course, there's no general and factored form here because these are just simple constant functions, degree 0 polynomials. All right, let's put those away and take a look at the next folder of functions. We've got polynomials that are of degree 1, and these are called linear functions. The first one is y equals x plus 1. And you'll notice in terms of the end behavior that this extends from bottom left to top right. I would say it starts down and finishes up. Some people refer to the starting place as being in quadrant number 3 and finishing in quadrant number 1. That's fine. That's another way you can describe that end behavior. And if you compare that with the next one, it's got different end behavior. This blue graph starts up and finishes down. And the reason for the difference between these two is because of the fact with the black graph, you have a coefficient of x, which is positive, whereas with the blue graph, you have a coefficient of x, which is negative. So with a positive leading coefficient, a linear function will start down and finish up. With a negative leading coefficient on linear functions, you will start up and finish down. Now you might be wondering about this third example here, and so it's not showing up right now because it's actually right in the same spot as the blue graph. So I'm just going to hide the blue graph, and now you can see the orange one. So the blue and the orange are actually the same graph. The difference is that the equation is in this form where we can see x minus 6 is a factor. And the relevance of the x minus 6 is that 6 is a 0. It is the 0 of this function. So you might be saying, okay, well, that's nice, but why would anyone write it in this other form in blue then? Well, if you notice the 2 on the end, the relevance of the 2, that positive 2, is the place where we cross the y-axis. So I would refer to this blue graph, the equation is in general form, whereas that the orange one, I would say, is in factored form. So factored form is particularly good for finding zeros, and general form is particularly good for finding the y-intercept. So next we're going to look at quadratic functions. So quadratic functions, if we take a look at the first example, we have a leading coefficient that's positive. It's a positive 1 multiplying x squared. So by lead coefficient, I mean the coefficient that's multiplying the highest power of x. Highest power of x is x squared here. Coefficient is positive 1, so positive 1 is the lead coefficient. And if you compare that with this one down here, where the lead coefficient is negative, you'll notice that the end behavior is opposite for these two. So when the lead coefficient is positive, it starts up and finishes up. And when the lead coefficient is negative, it starts down and finishes down. So that's end behavior. Now the other thing is the number and nature of the zeros. So with this blue graph here, you'll notice that the vertex is above the x-axis and this parabola opens up above that. So it never touches the x-axis. It doesn't factor, so we can't look at it in factored form. And there are no zeros here. So the minimum number of zeros, it is possible to have no zeros for a quadratic function. On the other hand, if you take a look at this black graph, you'll notice that it has 1 0. And the 1 0 can be easily identified from this form. So if I just hide that black graph and look at the green graph, it's exactly the same, but it's in factored form. So the x plus 1 squared corresponds to the 0 being at negative 1. So opposite of plus 1, minus 1, that's where the 0 is. Now there's only 1 0 for this particular function. Now if we take a look at this graph, which again, if you put it in factored form, it's maybe a little bit easier to identify the zeros. So you can see that one factor is negative x, and this corresponds to x equals 0, that's 1 0. And then there's a second 0 at x equals 3. So this just goes to show you that for quadratic functions, you can have either no zeros, 1 0, or 2 zeros. Now, when you have 1 0, I'll just note that I would call this a double zero because there's a factor of x plus 1 times x plus 1. There are two factors that multiply each other. And what it means is that when you have a double zero, you'll notice that it coincides with a local minimum or a local maximum. Contrast that with the purple graph, where you have two different factors. And what you'll notice that's different on the graph is that these zeros are places where the graph crosses the x-axis. And let's see if we can examine the same kinds of things going on with cubic functions now. So for starters, let's talk about y equals x cubed, which has a lead coefficient that is positive. And in this case, with a positive leading coefficient, it starts down and finishes up. And with this example where you have a negative lead coefficient, you'll notice that it starts up and finishes down. So that deals with end behavior. Now let's talk about the zeros. So the minimum number of zeros is 1. It is possible to have 2 zeros. So let me just hide the first one and focus in on this. So we've got 2 zeros there. Now, currently I have it in general form. If I change it into factored form, it's a little bit easier to understand, right? We've got a double factor of x here, x times x. That double zero corresponds to the graph touching the x-axis but not crossing it. Where you have the single factor of x minus 4 corresponds to a 0 here at x equals 4, where it crosses the x-axis. So 2 zeros, one of them is a double zero, one of them is a single zero. And that single versus double is called multiplicity. And finally, if I take this last one and compare it, and actually just put it into factored form, so I'll hide the other one, you'll notice that this one in blue has, just zoom in on this a little bit, it has 1, 2, 3 zeros, and they correspond to the factors of x, x minus 1, and x plus 1, and they're all individual factors. So since these are single zeros, it means that the graph crosses the x-axis for those places. So now we've examined all of the key features of cubic functions. Let's take a look now at the quartic. So now for the quartic, if we have a positive leading coefficient, then it starts up and finishes up, which is identical to the quadratics. And if it is a negative leading coefficient, then it is going to start down and finish down. So lead coefficient is what determines the end behavior. Now, as far as number of zeros, you can see that in the case of this green graph, we have no zeros, does not cross the x-axis, which is the same as the starting place for the quadratics. So notice that when we've got degree 2, degree 4, and if we were to look at degree 6 as well, we'd find the same thing. Minimum number of zeros is no zeros. It is possible to have a single zero. It is possible to have, let me just hide the previous one, 2 zeros. So this one is a triple zero. Let me just replace this with the black graph. This is in factored form. This triple zero, because it's an odd multiplicity, means that the graph crosses the x-axis at x equals 0. And x minus 2 as a single factor means that at x equals plus 2, we cross the x-axis. So in any case, just 2 zeros there. Let's take a look at the next one and hide the previous. So with this one, we have 1, 2, 3 zeros. You'll notice that one of the zeros is at negative 2. Single factor of x plus 2, single zero here, crosses the x-axis. Let's talk about the last factor here, which is x plus 1. Single factor of x plus 1, single zero at x equals negative 1. The graph crosses the axis there. And then this factor in the middle, this x minus 1 squared, it's a double factor here, it's a double zero here. You'll notice that the graph comes up to the x-axis, touches at that point, and then returns back down. So it corresponds with the local maximum, and there's not crossing of the axis in this case. Now, the last example, just to illustrate that Cortex can have up to, let me just zoom out so you can see the whole thing here. The maximum number of zeros is 1, 2, 3, 4. And so with the even degrees, you can have no zeros or 1, 2, 1 or 2 for quadratic, up to 4 for quartic. And so all the even degrees have the same kind of characteristics that way in terms of the number of zeros. Now let's go to the last one, which, and you're probably realizing now that the fact that it is degree 5, which makes it an odd function, it's going to behave in a similar way to cubics and linear, which is that, first of all, because it either needs to start down and finish up, that's if you have a positive leading coefficient, or if you have a negative leading coefficient, it's going to start up and finish down. It is definitely going to cross the x-axis at least once. So minimum number of zeros is 1. And that's the case here for this red graph. But of course, we could also have, if I just hide the red graph and focus on the blue one now, you'll notice here, if I just zoom in on it and touch that graph, you'll see that 1, 2, we've got 2 zeros. That's possible to have 2 zeros. It's possible as well to have 3 zeros. And so here's the entire shape of the graph. You'll notice that 1, 2, 3. We've got 3 zeros there. And it's possible to have 4 zeros. So let me just zoom in on that part. 1, 2, 3, 4 zeros. Or you can have up to 1, 2, 3, 4, 5 zeros. They're a little bit squished. So that completes the investigation of these polynomials of degrees 0 through to 5. And now let's make some notes to summarize what we've figured out. So here are the notes that we're going to make on these characteristics of polynomial functions. First of all, a polynomial function is a function that's in the form a subscript n times x to the n plus a n minus 1 times x to the n minus 1 plus, and so on, all the way down to a2x squared plus a1x plus a naught. Naught means subscript of 0, where n is a whole number, x is a variable, and a naught, a1, all the way through to an are real numbers. So here are some examples of functions that are polynomials, and then some examples of functions that are not polynomials. So polynomials include things like this, pi plus a half. And some people think that maybe this is not a polynomial function because we've got an irrational number there, but pi is just a number. Pi plus a half is just a number. So that would be like your a naught, that would be a constant function. So it's still a polynomial. If you have a polynomial that's in factored form, this is still a polynomial. So this would be a polynomial of degree 2. And also, if you have a polynomial in which there is one of the constants is a square root of a number, this is still just a number, so it is still considered to be a polynomial. This would be a quintic polynomial degree 5. So here are a few examples of things that are not polynomials. So when you have the square root of x, which is like x to the 1/2, when you have 3 over x, so this is like x to the minus 1, x squared plus y squared equals 25. This is not a polynomial function. So if you have x squared plus y equals 25, that would be a polynomial. But anytime you change the exponent on y to something other than 1, that's a problem. If the exponent on x is negative or fractional, decimal, then that is no longer a polynomial. And I'll just add one more to this list. So I notice that it's not included here. So I guess we'll call this G3. So G3 is when you have something like 2 to the x. So x can't be the exponent. It must be the base, and the exponent must be a whole number. All right, so let's move on. All right, so we're going to use this chart to identify the characteristics of polynomials of degree 0 through to 5. So first of all, constant functions are degree 0. You notice that they can, these are even functions, and we're going to be talking about the common characteristics between polynomials degree 0, 2, and 4. All of them being even, they have some common characteristics. The number of zeros is either none or infinitely many if the function is 0 itself. The end behavior is that it extends horizontally to the left and to the right. Domain and range. Domain X is real, and the range Y is that specific A naught. So what it looks like is this. So this is what it would look like if A naught was positive, and of course if it was negative, it would be down here, and if it was 0, it would be right on the x-axis. So this is the general graph. Polynomial of degree 1 is called a linear function. It's odd, and so we're going to be looking at the common characteristics of odd functions, polynomials degree 1, 3, and 5. The number of zeros is at least 1 and maximum 1 in this case. The end behavior, it either starts up and finishes down or starts down and finishes up. So once I get my sketches there, I'll explain the difference between the two. Domain and range. X is real for the domain, the range Y is real. And here are a couple of linear functions. Y equals 2x plus 1. So you'll notice that when the lead coefficient, the coefficient of the term that has x to the highest exponent, when that's positive, it's going to start down and finish up. And when you have a polynomial whose lead coefficient is negative, and you're looking at odd functions, it starts up and finishes down. And now let's take a look at quadratics. So quadratics are even. They are polynomials of degree 2. The number of zeros can either be 0, 1, or 2. And the end behavior is it either starts up and finishes up, or it starts down and finishes down. The domain X is any real number, and the range is Y is real, but Y is less than or equal to its maximum value, or Y is greater than or equal to its minimum value. So here are some pictures we're going to look at in just a minute. But by the way, for end behavior, what I noted before was that the end behavior is dependent on this lead coefficient. So just take a look at that. That will help you determine the end behavior. You may want to add that as a note at the top here. Okay, so now let's take a look at 3 situations. So you notice that this green graph has no zeros. This blue graph has 1 0, and the red graph has 2 zeros. And so number of zeros can be like so. You'll also notice in terms of end behavior, it either starts up and finishes up. That's the case here. That's when the lead coefficient is positive. Or starts down and finishes down, and that is when the lead coefficient is negative. All right, so now looking at cubics, which are odd functions, polynomial of degree 3. The number of zeros has to be at least 1, maximum 3. And so the end behavior is starts down and finishes up, or starts up and finishes down. So what you'll notice is that all odd functions have at least 1 0, and they have this end behavior that starts down and finishes up, or starts up and finishes down, depending on the lead coefficient. If the lead coefficient is positive, it starts down and finishes up. And if the lead coefficient is negative, it starts up and finishes down. The domain and range of all odd polynomials are, the domain is going to be x is real, range is going to be y is real. And for a sketch, so you can, I know it's a little bit small here, but you can take a look at the Desmos activity to review specific examples with specific formulas, specific equations for these functions. But you can have 1 0, you can have 2 0, looks like that 0 is a double 0, or you can have 3 zeros, as is the case here on the green graph. And you notice that I'm also showing that it can start down and finish up, or it can start up and finish down. This one has a lead coefficient that is positive, this one has a lead coefficient that is negative. So now polynomial degree 4 is even, and Cortex can have 0 up to 4 zeros. So what you'll notice is that for even functions, they can have no zeros up to a maximum of whatever the degree of the polynomial is. The end behavior is also the same for all even polynomials, which is they start up and finish up, or they start down and finish down. This is the case when the lead coefficient is positive. This is the case when the lead coefficient is negative. Also, in terms of domain and range, you're going to find that x is real for all polynomials. The range is going to be the same for all even polynomials, which is y is greater than or equal to the minimum value, or y is less than or equal to the maximum value. And now we want to draw a sketch for all those different scenarios. It's a little bit tight for room, but here are some. So I don't believe I have one that represents number of zeros being 0, but just imagine this purple one was shifted up a little bit. We could have no zeros, or 1 0, or 2 zeros, or 1, 2, 3. This yellow one has 1, 2, 3, 4 zeros. So up to a maximum of 4 zeros. And finally, we have a polynomial of degree 5, which is an odd degree. This is called a quintic. And the number of zeros has to be at least 1, maximum 5. So notice odd polynomials have to have at least 1 0. Maximum number of zeros is equal to the degree of the polynomial. The end behavior is like the end behavior of all other odd polynomials, which is that they start down and finish up, or they start up and finish down. So this is the case when the lead coefficient is positive, and this is the case when the lead coefficient is negative. Domain and range is the same for all odd polynomials, which is the domain is x is real, range is y is real. And to get a sketch of these possible situations, there are so many. So you may want to go look back at the Desmos activity to see all of those more up close. So it looks like this one has 1 0. It looks like this one has 1, 2, 3, 4, 5 zeros. That's the maximum. This one has 1, 2, 3, 4 zeros. This one has 1, 2, 3 zeros. This one has 1, 2 zeros. So as you can see, number of zeros can be 1 up to 5. Notice that some of them start up and finish down. Some of them start down and finish up. So trying to do a little sketch that shows all of those different possibilities. So that completes the lesson. Hope that helps you in your understanding of characteristics of polynomial functions. Thanks for watching and have a great day.